is, why don't we test it now? Let's see. How do I get back here? Okay. Now, good? Okay, great. So I want to talk a little bit about community, and I just want to highlight some of the talented people we have. We have over 12 million registered users, so you can't do it justice, but I just want to give you an idea of some of the really unique and interesting people we have. Vlad is a really interesting story. He got a PhD in physics from Berkeley in quantum Monte Carlo simulations, and ended up working in the IT department of a debt collection agency as the job he could find, which, as you could imagine, right, is very non-fulfilling as a job. So he found Kaggle and used it as a way to kind of keep his, mental capacity in challenge. Found a competition where of segmenting cars for Carvana, and you may be familiar with the UNet algorithm. He took the UNet, made an improvement to it, won the competition, published a paper, presented at a conference, and then ended up at Lyft as a senior vision engineer. This is Andrada. She's from Romania. She started doing Kaggle Learn courses as a way to improve her data science skills, entered some competitions, and then realized, what her passion was creating very high quality exploratory data analysis notebooks to share with other people and very high quality visualizations. She rose to very high prominence in the community because of this. And then in addition to her day job, HP, Z by HP found her and then hired her as a global data science ambassador. This is Nelson. He's a professor in Uganda, also has a PhD in computational astrophysics. He says the job is boring, so he does data science work on Kaggle and other places as a way to keep his mind interested. He's also a Alan Turing Institute Data Science and AI Educator Fellow, and Kaggle awarded him a grant recently for his work on navigating linguistic diversity in the African context. Really difficult, where you have so many languages, and then so many languages that connect, and then all sorts of people will blur those lines, and so how do you do natural language processing in a context like that? And then this is one of my favorite examples. This is Mikkel. He's from the UK. He started Kaggling when he was 14 years old. In fact, Kaggle had to change their rules because it used to be you had to be 18 to win a prize, and then Mikkel won, so we had to kind of figure out how to get him a prize, and then ended up changing our rules. He ended up, so we have global rankings of people that place in competitions. You get ranking points, and he ended up 31st. So we have a community. It was probably 7 or 8 million at the time, but he ended up in 31st place, which was kind of a conundrum because companies wanted to hire him, but he was in high school. And in fact, he forwarded me an email he got from a recruiter just before he was 16, and he gave me permission to share this, but the email said, Mikkel, apologies, we have to cancel the phone interview for later today. I misread your resume and thought that you had 15 years of machine learning experience, not that you were 15 years old. So he's currently at Cambridge studying computer science and mechanical engineering, and I think graduates this year. The article at the bottom was posted in Wired magazine. It says he can't drink whiskey, but he can program a neural network. So I bring this up really just to highlight the fact that Kaggle, the competitions and the other resources are a magnet for very talented people who are motivated to work on interesting problems from different domains to keep their minds sharp, to learn. And we have many, many people like this in our community. So before I talk about specific competitions that we run in the science domain, I want to talk a little bit about how open source competitions can drive the state of the art. So one of the early competitions that Kaggle ran was to identify pockets of dark matter in the universe. And if you look at the universe, you have galaxies that come in, and depending on the orientation, they'll have, they could be round or they can be skewed and have ellipticity. And what dark matter does is as the light comes in, it skews the shape of those galaxies by gravitational lensing. So if you have a pocket that has all of these weird kind of like higher than expected ellipticity, you can infer that there's dark matter in between, here and those galaxies. And so this is kind of represented by the purple. It becomes much more difficult when you have multiple pockets of dark matter that are skewing the light in different manners. So we held a competition, and it was hosted by NASA, the European Space Agency, and the Royal Astronomical Society, and they wanted to see, can machine learning beat, the traditional algorithms? And within a week of the competition, so this represents our leaderboard score. Within a week of the competition, a gentleman by the name of Martin O'Leary, who was getting a PhD in glaciology from Cambridge, beat the state of the art. And it was so exciting for the organizers that they had a press release on the White House website that said, the world's brightest physicists have been working for decades on solving one of the great unifying problems of our universe. In less than a week, Martin O'Leary, a PhD student in glaciology, outperforms the state-of-the-art algorithms, which is fantastic. Unfortunately for Martin, there were still 2 months left in the competition. So this is the leaderboard over time. You see a team makes an even bigger jump, and then other team, Martin, gets better, and then some other teams jump in, and the leaderboard score gets to the bottom, and it was finally won by a particle physicist and a cosmologist. And this kind of behavior highlights some really interesting things. So I guess the first thing is that in open source competitions, non-domain experts frequently beat the state of the art within the domain. And that's a little bit counterintuitive, but I'll explain why in the next slide. I've been at Kaggle for 6 years, and in that time we have launched about 200 featured competitions, and I know of only a single instance where the community did not beat the state of the art in that was, at the time when the competition was launched. And in that instance, it turned out that the published state of the art had used the test set labels a bit liberally to tune their hyperparameters. So in other words, the state of the art was overfit, and and indeed the community found the actual state of the art in that instance. The other thing that's interesting to note is we have a good deal of empirical evidence that suggests that these open source competitions saturate all of the signal that's in a data set. We can do ensembling of different models, and we find that we can maybe improve the best scores by a little bit, but effectively what that says is with a given data set, the community will find a model that extracts the maximum signal from that data set. So, all right, what makes crowdsourcing so powerful? So yeah, I think it's one of the main things is the competition effect. If you're a grad student and you beat the state of the art and you get your name in a White House press release, yeah, you're good, you're done, right? Yeah, you're happy. But if you wake up the next day and some team has leapfrogged you, you're going to get back to work, right? Because you want to win that competition. So that competition effect drives people to press forward. And it's also part of that 4 minute mile effect. When Roger Bannister broke the 4 minute mile, right? No one could do it, and he did it, and a whole bunch of people did it, because in your mind, for example, as a competitor, you go, oh, there must be something that they're doing. I need to figure out how they got that score. So those effects really drive the state of the art forward. They tap into a much broader human potential, right? Like so many different people across the globe with different diverse backgrounds working on the problem, as well as the computational. So I joked about my 256 megabytes of RAM that cost $10,000. In the mid-90s, computation was not ubiquitous like it is today. Now everyone has some computation. A lot of people have a lot of computation. Why not tap into that broad resource pool? Interestingly enough, people from different domains don't have blinders on. Let's say there was something that didn't work 4 years ago. In your mind, if you're in the field, you're like, oh yeah, that was tried 4 years ago and it didn't work. Well, people that aren't in the domain, they don't know what doesn't work. So they're going to try pretty much anything. If it works, they'll use it. We kind of refer to it as empirical validation. It's one thing to have a theoretical, yeah, this should work, should be the best. It's another thing to prove it on a leaderboard. And also the people collectively have exposures to a much broader set of tools and ideas. So then I think the last point, which is also very powerful, it's a bit counterintuitive, but most Kagglers do not play to win. Obviously, everyone would like to win, but most Kagglers play to learn. They're in it to either exercise their brain, work on a challenging problem, or improve their machine learning skills. So during competitions, and this is so counterintuitive, during competitions, people will actually share their ideas. They'll say, hey, this worked. Hey, this didn't work. And so other teams will take that information and adopt that. So it's this kind of this collaborative improvement. While at the same time, it's competitive. So you're kind of getting the the best of both worlds in that regard. All right, so let me talk about some science competitions on Kaggle. And I know we're a little behind just because of some of the disruption. So I'll probably mostly spend my time on this one because I think it's the most interesting one. But this was a competition we ran in mid-2020 And it's my favorite for a couple of reasons. So this is obviously right in the middle of the pandemic, and it was a competition to predict mRNA vaccine degradation rates. And you can see a paper that was published in Nature Machine Intelligence that came out of this competition. So we're proud of it for two reasons. One, most competitions have a 3 to 6 month lead time just to get everything ready and to get it launched. And then we'll spend 3 months on the competition. Well, why 3 months? Well, you know, most people that participate in these open source competitions, they're doing it part-time, right? They're not, this is not their full-time job. So they're doing it nights and weekends and mornings and lunch breaks. And so we need to give them enough time to engage. Well, with this one, we launched it from the time that the lead came in, launched it in 3 weeks, which is blazingly fast when you think of all the approvals and for hosting data and whatnot that have to come in. And then the competition only ran for 3 weeks. So it was a 6-week lead time. And in that 3 weeks, I'll show the results in a second. So the second point that was interesting, it was a dual crowdsourced competition. So there's this site, maybe some people are familiar with it. It's called Eterna. It's kind of an online game simulation where you can build sequences, and then the simulation will tell you the properties of these sequences. And so there's an Eterna community of a few hundred people, and they were tasked with building RNA sequences between 100 and 130 nucleotides that were the most stable. So they built 6,000 of these nucleotides. And then what the host did, they took those, they built those structures and then measured the reactivity in the lab. So then they had real data. So then they hosted this data on Kaggle, and they also gave the 1D structures as well as the base pair probability matrices for each of those molecules. And then the Kaggle community, they were challenged was improving degradation prediction models by predicting RNA degradation profiles and shape reactivity. So it was, they had a kind of a starter reactivity model or degradation model. It's like, okay, here's real data, now build a stronger model. And within 3 weeks, the competitors beat the state-of-the-art DEG score by about 25%. The score was RMSE, so fairly significant. So you can see a couple of stars. The red and the yellow star are where the state-of-the-art. That purple star was a public notebook. So again, somebody shares like, hey, here's my work. Anyone can use it to improve. And then those blue dots that point downward, those were the best scores. Again, lower is better. And that black dot is the experimental error. When it was all said and done, 41% of the nucleotide level predictions from the winning models were within experimental error of the ground truth measurements. So, they were very close in almost half of the predictions. I said, well, does this generalize? So after the competition, the hosts took these winning models, and then they predicted against our mRNA molecules that were between 500 and 1,500 nucleotides in length. And they found that these models actually improved the state of the art for much longer. So they generalized to much longer sequences. So just going to mention this one really briefly. So this was a competition we had to predict, so given a molecule, predict the atomic coupling between atoms within a molecule. I just want to point this out that this was, as far as I can tell, the first documented use within this Kaggle competition where somebody used a language model, a transformer language model, to encode molecular properties to make predictions. So, Kaggle is a place where all sorts of great ideas come up because, again, somebody's going to go, hey, why don't I try this? And they give it a try. Let me just skip this, really briefly say we've done dozens of competitions in physics and astronomy from gravitational waves. We've done a project with SETI to detect anomalies from radio signal data. We've done dozens of medical, a lot of segmentation or detection competitions. We've done a number of in molecular biology, both the kappa prediction, which will be talked about next. Novozyme did a enzyme stability prediction. And we've done mechanism of action competition. So lots of really fun science competitions. So let me just talk about some challenges, and these are real and these are important. One of the biggest challenges is I would call the human aspect. and this is real, right? If you have a data set, you want to be the one that figures out, solves that problem, or publishes the paper, right? Or at your lab. It's actually kind of psychologically difficult to say, I'm going to open it up and have a community help me solve this problem. So, there's a natural hesitancy in many organizations. So you really have to see that the benefit that you get outweighs, the disadvantage of not being the sole author of a publication. Some people are concerned that solutions aren't elegant. When you have control over your modeling, you can say, I want a very simple model. I want it to be very explainable. And if I have an open source Kaggle competition, they're going to ensemble, and it's not going to be clean and elegant. I would say what we found is winning solutions always have elegant parts of that, and they may ensemble different models to improve their result. But most hosts end up taking, they have a lever that they can take bits and parts of the solution and say, okay, I want the best predictive ability as possible, or they can say, okay, I'll just take the parts that are the most explainable. And then the other thing, it actually can be a little bit more challenging if you want to publish. The reason is you can have people from all over the globe, from all different backgrounds. You can have a high school student that's winning a competition. So if you want to publish a paper, you have to be a little bit more diligent about herding the cats and getting the paper published. Probably the next biggest issue is the data has to be private. We have to have private ground truth. As you can imagine, if the data is right in science, we pride ourselves with having open data, making data public. But yeah, if the labels are public, someone will find them. So this often is a challenge for hosting these. There's a sweet spot where these competitions run really well. If it's terabytes of data, that's kind of beyond the reach of most people, so you won't get very much participation. If it's 100 kilobytes of data, as I mentioned, Kagglers are very, very good at extracting all of the signal out of that. You don't want the competition to end in 20 minutes because somebody got the absolute best model possible from your 100 kilobytes of data. So the successful competitions that we host are typically 500 megabytes to 500 gigabytes in total data size. Sometimes it can be larger, supplemental data or whatnot, but that's about the sweet spot. And then leakage, you have to be super careful. If you're in a lab and you have your, say, images and you have the ground truth, like cats and dogs, like cat 1, dog 1, cat 2, right? You're not going to use that in your model that you're building. But if you publish that in a competition, the competitors will use that. So you have to be really careful about all the subtle ways that you can leak information in your data, and be careful about that. Okay, so let me just spend a minute talking about Kaggle. We are really working hard to keep up with advances in the field and doing things like allowing code competition. So instead of predicting just pure predictions against the target set, users submit a notebook. And then we rerun that notebook and make predictions. We can do it on a completely unseen test set so that they're not overfitting to the distribution that found in the test set. That has some advantages too if you don't want people using huge monster ensembles of different, somebody that has a bank of 20 GPUs. In this way, because the notebook has to rerun within the Kaggle environment, it kind of constrains the size of the model that people can use, which is beneficial. We've recently made it much easier if you have an evaluation metric in Python, for example, much easier to integrate with the system. Before, we had to code custom metrics in C# in our backend. And then one other thing I want to mention, and this has not been publicly announced yet, but I did get permission to mention it here. Within a week, we're going to be announcing Kaggle grants, and the idea here is for any academic, nonprofit, or research institution that has a problem they think would make a good Kaggle competition. We have a grant program that will run quarterly. You can apply for that. There'll be some criteria. If the problem meets that criteria, we both waive any of our service fees that come along with launching a competition, and then we'll also help sponsor prize money for that. Because it's not public yet, I don't have a website, but if you're interested, you can send an email to researchgrants@kaggle.com and just say, hey, I saw Walter's presentation. Just can you send me the link once it becomes live, and we'll make sure you get the link. And I definitely recommend that you check it out. So let me summarize. This was my favorite quote until about the last year from Alvin Toffler. He was a futurist. He said, "The illiterate of the 21st century will not be those who cannot read and write, but those who cannot learn, unlearn, and relearn." And I love that because we live in a world where there's just so much information, and you can teach yourself machine learning or whatever. But gosh darn it, Alvin, the last few years have been really tough for people that have been trying to keep up with machine learning. So this is the number of papers that were submitted to NeurIPS. And we're looking at 8,000 papers just submitted to the NeurIPS competition, NeurIPS conference. It's impossible to keep up. You can't keep up with the papers. You can't keep up with the tools. A year ago, did anyone know about Stable Diffusion? Maybe you heard of it, but you had no idea of the potential. Large language models, every 2 weeks, there's a major breakthrough. This is my full-time job and I can't keep up. My head is spinning, right? I feel for anyone that's right in any other domain that wants to use machine learning. So wouldn't it be better, right, for instead of us trying to keep up, to get 1,000 machine learning experts looking at all of these things, looking at these papers, looking at these tools, trying these tools, and then focusing in on our problems. And that's the idea with these open source machine learning challenges. So, I would say I thought a lot about this, and I firmly believe now that the wisdom of the crowd becomes much, much more valuable the faster a field is progressing. And I think we're in a fast progressing field. So I would absolutely recommend, if you have a problem that you think could be useful and could be valuable in an open source setting, to consider that. And with that, I will say thank you, and we'll open it up to questions.
Thanks for a great talk, really inspiring. So is it always just optimizing for performance on the benchmark, or do you ever consider how efficient someone got to the solution? Because you've got sustainable computing to kind of drive these things down. So is that ever a consideration?
Yeah, absolutely. And to your point, more and more so. So part of the notebook submissions is it allows us to constrain how much compute is actually used during the inference, at least. And we can set that. So we can't get down to super, like if you say, oh, it needs to be 100 microseconds per inference. We can't get down to that resolution, but we can say, yeah, if you have 1 million data points you want to inference, but you only want to give people an hour's worth of compute to do that, we can do that level of granularity. We've also recently just updated our platform to allow actual model checkpoint as a submission instead of the predictions. So that's going to give us the ability to have a lot more granular timing. We have a lot of our competitions where we have hosts that are interested in efficiency. What they'll do is they'll run the competition, they'll give an award based on the best score, but then they'll open it up to people that want almost like a secondary bonus prize for efficiency, and they'll submit their code, a Docker containerized code to the host. The host will run it on their, very reliable piece of hardware, constrained hardware, and then they'll award a secondary prize based on efficiency. But yeah, appreciate that question. I'll say one more thing about that is it's very difficult to optimize for both, right? You have to have a curve in how you figure that out. So it becomes a little bit more difficult. So we usually try to separate those. Yeah.
Hello, great overview. Is there a reason why there was this Wired article a few years back about a Kaggle competition that was in person, and there was a Google AutoML team there, and they were #1 on the leaderboard for most of the time. But apparently a team beat them, so it got pushed to second. The team was cheered apparently. But I'm curious, what's your take if someone's considering just using Google AutoML, which is somewhat trained and benchmarked against past Kaggle competitions, versus you can do that much more quickly than say like a 6-month proper Kaggle competition. So I'm curious about that trade-off or the differences.
Yeah, AutoML is fantastic for problems that are more run-of-the-mill or have been solved. So if you have a very large tabular data set, AutoML works great. AutoML solutions can be expensive, right? There's a lot of open source and free in AutoML. So it really does depend. The advantage of a lot of AutoML solutions is you get both the training, and then you have the ML ops, like it's already engineered. So now you have the interface where you can then do the inference. Whereas if you have a Kaggle competition and you get a winning model, you have to build that into some sort of platform to give predictions. I would say in research, it's probably usually better to have people figuring out what the best. If you're in a setting where you need to open up your predictions, like you want to have a website where people can submit the raw data and it gives predictions to them, AutoML could be a quicker solution because now you're not spending the engineering time implementing the solution. But I'll also say there's many data formats where AutoML just can't compete yet.
Really cool, thanks. I was wondering, you mentioned how sometimes state-of-the-art overfits. And I was wondering if you know how often this happens with the community, so the winners of the competitions you host, if you have any stats on this.
Yeah, there was a very large-scale analysis done by statisticians within Google on the Kaggle leaderboards, and what they showed is, on average, the Kaggle competitions don't overfit. There are teams that overfit clearly because we have a public leaderboard that's maybe 20% of our data, and then the private, and so people can get a score, and a lot of teams will try to optimize to that 20%, which leads to overfitting. But the experienced Kagglers, they do local cross-validation and whatnot, and they're much smarter about that. So yes, there are people do overfit, but on average, there's no empirical evidence of systemic overfitting in these open source competitions. That's a great question.
I would love to see a figure of how the leaderboard changes when you go from the leaderboard scoring and the actual live test set.
Yeah. I mean, so in this case, this shows here. Yeah, you can see the people did better on the public leaderboard, which is the x-axis, getting down to 0.25, where on the private it was only 0.35. So people got a better score on the public, on the score they were getting as they made their submissions. So they did overfit probably a little bit, but this one was a little bit different, just probably because of the time. It was so compressed.
Thank you.
Yeah.
Hi, that was awesome.
Oh, thank you.
I'm kind of curious how much you guys actually do with the models that are submitted. So is there a meta model that works better than any of the submissions of the Kagglers? Do you consider doing that? Would you do that yourself, or would you find someone else to do it?
Yeah, so love the question, great question. So we have done time and time again, every once in a while, we'll take a competition and we'll take all of the submissions and we'll look for high scoring submissions that are that have the least correlation, and then we'll ensemble those together, and almost always we get a little bit of improvement, just a little bit of the score. So so that tells me, okay, there's a little bit of room, but to have a meta model of multiple teams probably doesn't make sense. But in terms of, let's say we have 3 winning teams, what the winning host will typically do is, they may say, oh, they may pick the 3rd team because it may be a simpler model, it may be easier to implement. So what's nice about having multiple teams win is you get different approaches, and then the host can pick and choose the ideas from that. So oftentimes it's actually not the winning model that a team submits, but very often hosts will say, oh, I love how they did the data pre-processing. Oh, I love how they did this. And they'll take parts and pieces and then they'll just incorporate that into their pipeline rather than incorporating just the winning solution. So it's just as often and not, it's not the actual model checkpoint, it's all of the ideas that are then incorporated into whatever the host of the competition is doing.
So from the model perspective, it seems like it's a good way to find orthogonal solutions that could contribute to a better model.
Absolutely. Yeah.